Hi, my name is Simeon Withier, and I will be presenting our work titled Greedy Networking and Cryptocurrency Blockchain. This work is presented on behalf of myself and my co-authors, Pranav Chandramouli, Ziabo Zhou, and Zhengyun Cheng. This work is supported by the National Science Foundation under grant number 19-22-41-0. So to begin, I'd like to talk about the motivations for this work. The networking portion of a cryptocurrency is very important as it is responsible for the synchronization and information propagation required by the cryptocurrency operations. These consist of the reliability of information transmission, the latency and throughput for fast information propagation, as well as ensuring that the peer selection and network topology are reliable and efficient in communicating with others on the network. In this work, we explore the rational and incentive-driven networking strategies. We define the rational strategy as any behavior that optimizes the user's income irrespective of the fact that a user may deviate from the protocol specifications. Similarly, we define greedy networking as the behavior in which a node will continue increasing its connectivity for an increased financial gain when mining. Consequently, this may also be unfair and potentially destructive to the rest of the network. The main motivator for this project can be summarized into a single sentence. When we started this project, we thought that the rational strategy is equivalent to greedy networking, where greedy networking is maximizing connectivity and the rational strategy is maximizing profit. The main motivator for this work is what happens when a mining node starts connecting to more nodes. We know that there will be more connectivity in the network and information will be propagated faster, but we do not know if the rational strategy is the same as greedy networking. If they are the same, then the network will be more connected and potentially too connected, but if they are different, then some other strategy exists that will optimize the connectivity for a rational peer-to-peer node. Our work is also motivated by an online Bitcoin forum asking about how to increase the number of peer connections beyond what Bitcoin supports. While the responses were generally helpful, one response came in by a Bitcoin developer, Peter Wale, stating the following: "Please don't change this, as there is no need. Connectable peers on the network are a scarce resource and essential for decentralization. If people go and try to connect to all of them, like some sites do, then we'll very quickly run out." This statement motivated us to research the problem a bit deeper. However, it still does not give us insight about the rational strategy for incentive-driven users, since it is true that more connectivity will mean faster information delivery. It may be detrimental to the network if there are too many greedy users. Looking more on the incentive side, we found another quote by a user named Claris, stating that many of these services attempt to connect to a large portion of the listening network and gain insight into the chance of transaction confirming, implying that the greedy networking strategy is indeed used by some entities to gain insights about transaction confirmations, among other observations. So in this work, we wanted to analyze these statements a bit more rigorously. We found that self-interest-driven nodes or miners are actually not incentivized to arbitrarily continue increasing node connections. Of course, this is dependent on the hardware and other parameters, but we come to this conclusion by computing the optimal number of connections in a variety of real-world Bitcoin node instances. We are the first to systematically analyze the greedy networking incentives used in cryptocurrency applications. To give a bit more background, Bitcoin uses proof of work. It was proposed by Satoshi Nakamoto in 2008, which has influenced the cryptocurrency era for later research and development. The underlying consensus protocol is responsible for maintaining the functionality and availability of the respective cryptocurrency, and proof of work is currently the most widely adopted and rigorously analyzed consensus protocol to date, which has influenced later R&D in optimizations, privacy improvements, as well as attacks and defense measures on the protocol. So how it works: mining consists of taking the latest block header, which includes a timestamp, previous block hash, the nonce, and some other data fields. The block header is hashed twice using SHA-256, which generates a kind of fingerprint for that particular set of data fields in the header. The hash output is checked for validity, which includes counting the number of 0 bits in the starting sequence of the hash, and if it achieves a predefined threshold, known as the block difficulty, then that block is immediately broadcasted to the rest of the network. Otherwise, the nonce is incremented and the process repeats. The block difficulty is adjusted every 2 weeks according to the hash computational power of the network, such that the block is mined approximately once every 10 minutes. With blocks repeatedly being solved and added to the blockchain approximately every 10 minutes, transactions can be published within the blocks, and the block solver will be awarded with a special transaction that mints new currency and incentivizes the mining process. So mining is the procedure of repeatedly accepting new transactions into a block, then trying to compute a random number that makes the hash of that block numerically small. This is a race condition, so any optimization to get blocks faster will give the miner greater probability of solving the next block. And upon being solved and broadcasted, all the participating nodes in the network will verify the authenticity of the block, then store that data locally in their block database. The broadcasting process is only possible because the nodes operate as a peer-to-peer network, meaning that if data is sent, all your adjacent node connections will receive that data, verify it, then forward it onward to their adjacent connections, until every node in the network has seen the data at least once. In this example, we can see the timestamps of the block after each hop. We denote the block propagation time as tau, and by keeping this block propagation time low, the miners will have more time to mine on the next block, thus increasing the probability of solving it. So let's say, for example, that a block is solved by the leftmost node in both of these diagrams. You can see the leftmost figure where the block propagated to 3 other nodes before reaching the miner. This delay in block propagation can be seen as the time that the miner has been mining a stale block, and if the miner was to find a block during this time, then the miner risks losing the reward because of the fork that it causes. Compare this to the figure on the right where the miner has more connectivity, so the block propagation takes significantly less time to reach the miner, and the miner can begin mining the up-to-date block sooner. Another big motivator for this work is the fact that Bitcoin has a limit of between 10 and 128 peer connections per node. 10 that are outbound, meaning initiated by our subject node, and 118 that are inbound, meaning initiated by others. By default, Bitcoin has inbound connections disabled, meaning that these nodes only ever connect to 10 other nodes, and there is little to no literature explaining why these numbers were selected. Regardless of the situation, the connectivity is dependent on the reliability of information delivery. To give a little more perspective on this, we experimentally ran a Bitcoin Core public node in its default settings for a few months to measure the peer connectivity. We did enable incoming connections, however, when we plotted the number of connections during that time as a cumulative distribution function, we found that the distribution of node connections stays at approximately 32 despite this number being arbitrary according to our setup and networking environment. While our node could have connected to 128 other nodes, it remained at around 32 connections for a majority of the time. We denote the number of peer connections as X, and this is the aggregate of outbound and inbound connections. Then we formally define greedy networking and the rational strategy by introducing a model and framework so that we can analyze these strategies more rigorously. Essentially, we have a function f which returns a sensing value dependent on x, again where x is the number of connections, and f is some sensing parameter in the cryptocurrency. We then use g to transform the sensing measurement into a monetary value of Satoshi per hour, where 1 Bitcoin is equivalent to 100 million Satoshi. So for example, let's say that f is the block propagation time, then f of x will return the number of seconds that the block has been propagating for, in this particular instance, and g of f of x will return the mining monetary value associated with losing that many seconds when mining. You're going to see us apply this mathematical framework to our real-world experimentation in the next few slides. By quantifying g of f of x, we can reselect x, which is the number of connections, as a sort of feedback loop that tweaks our connectivity according to the data that we're fed in. What we need to do is take the relevant real-world data and apply them to our equation as variables. We consider 3 sensing measurements: the hash rate of the miner, which we denote as alpha. It's the computational power of one miner in the network. Then the block propagation time as tau, which is the number of seconds mining on an outdated block while the latest block is still propagating to us as x increases. This reduces tau due to higher connectivity. We also include the power cost to run the node, rho, in kilowatt hours. And we find that as x increases, rho also increases since the power consumption used to run the mining node has more messages to process in a software instance. We define f to be the vector containing the 3 functions, alpha of x, tau of x, and rho of x. While we define just 3 parameters, the framework can be used for additional parameters, so this framework is not limited to our selection of alpha, tau, and rho. In order to use our framework, there needs to be a way to convert from the parameter's default unit into one that is consistent. That's why we include a conversion function, g, for each parameter. For example, alpha is initially in hashes per second, tau is initially in seconds, and rho is initially in kilowatt hours. After applying the g function, we are able to get each unit into Satoshi per hour, where Satoshi is 1/100 millionth of a Bitcoin. So we'll go through each parameter and define its conversion. To start, we'll look at alpha, the mining income derived from the hash rate. We define our conversion function as simply multiplying the mining hashes per second with the probability that a single hash is a valid block, and the reward for mining that block. So for consistency across parameters, we multiply by 3600 to get the unit of Satoshi earned per hour. And I highlight these variables in a table to make it clear which ones we're using for this particular parameter. So for example, if we compute 1 million hashes per second, and the probability of finding a block is 1 in 1 million, and let's say gamma is 6.25 Bitcoin, then we can expect 6.25 Bitcoin every second. Of course, the probability is significantly higher, but for the sake of example, this intuitive definition will help to highlight the following definitions. Next, we consider block propagation time, the time at which the latest block is being broadcasted through the network from the time that it was initially solved. Our miner will actually be mining an outdated block during that time. Therefore, this is a monetary loss that is computed with the same equation as with hashes per second, but by multiplying it with the negated block propagation time and dividing it by the block solve interval for unit consistency, we can effectively convert between time mining a stale block and Satoshi per hour. And again, the variables used are circled in the table below. Next up is the power consumption of our node, rho, which is computed by multiplying the electric exchange rate with the measured power consumption and dividing that by the cryptocurrency exchange rate to convert from fiat currency back to Satoshi per hour. There's many ways to derive or estimate the power consumption. In our experimentation, we use PowerTop, which does a good job of estimating the power consumption, but any monitoring device can be used. So with our mathematical framework defined, we wanted to talk a bit about the implementation. We apply it to the real world to experimentally validate our work, and this was done by modifying the Bitcoin source code and adding a new min connections configuration parameter, which basically grants us full control over X, then generating a log entry every second for 444 days, thus generating 88.8 gigabytes of logging data. For mining, we use 2 CPUs, 1 GPU, and 2 application-specific integrated circuits, or ASICs. Here we plot the block propagation time with respect to X and vary the number of random node connections between 1 and 512. The random block propagation time can be measured since we have the block's timestamp data field for when the block was solved, and the timestamp from when our node received the block. By simply taking the difference between these two timestamps, we can effectively measure the block propagation time. From this data, we find that blocks arrive approximately 11.77 seconds faster on average when the node is connected to 512 nodes as opposed to just one. Since this is an empirically random experiment, we also wanted to analyze the variance and the distribution as shown to the right. We see that the more connections we have, the smaller the variance is, which directly impacts the confidence intervals. Since we've established the equations to convert from our sensing parameters into a monetary value, we simply compute the summation of the parameters and take the argmax of the utility function to get the optimal number of connections, which we denote as x hat. On the right, we visualize how our utility function changes with respect to the number of connections. The argmax peak gives us an x hat value of 16.87 pure connections for this particular mining instance. Here we apply the framework to our mining instances. This allows us to put a numerical value on alpha, tau, and rho, as well as the other variables. This table computes the optimal number of connections, x hat, for each mining device. From this, we can see that the x hat varies according to the mining device. It's worth noting that there are a lot of moving parts in these calculations. For example, the exchange rate or the price per kilowatt hour or temperature of operation even, etc. We did our best to maintain consistency in all measurements and found that in general, the better performing devices typically yielded a higher X hat value. And again, X hat is the optimal number of connections that maximizes profit when applying our framework. The main takeaway from this is that the X hat actually exists, in that as opposed to greedy networking, where miners arbitrarily increase their connectivity, here we've computed an optimal value, some finite number that is the rational strategy for our framework. And so to go back to our original question, is greedy networking the same as the rational strategy? And our answer is no, it is not. We'd also like to touch on the security relevance of our work. Our proposed rational strategy often diverges from the default Bitcoin protocol. If X hat is large, this goes back to Peter Wiley's comment about excessive connectivity being detrimental to the network. Likewise, this limits the availability of connections for benign nodes. It also causes excessive networking overheads and a diminishing return of a slightly more efficient block propagation time at the cost of many redundant broadcasts. In this strategy, we've shown the situation where some miners are incentivized to deviate from the default protocol, which may open up further issues. As future work, it would be interesting to analyze the congestion when multiple miners follow the rational strategy. This may give insight about some Nash equilibrium behavior that optimizes the network for all nodes rather than just those who are greedy. In conclusion, we proposed a framework to study greedy networking and the rational strategy. We find that these two strategies are not the same and that there is a finite optimal number of connections. This varies with different parameters, and we tried to capture these parameters. We are the first to systematically analyze greedy networking and cryptocurrency, and this work sheds light on such behaviors to facilitate further research in advancing and aligning the incentives for blockchain networking.